Assalamualaikum and hello. My name is Siti Emilia Akilah binti Omar. Our group has selected question number 2, which is aircraft autopilot control system. This control system is created especially for unmanned aircraft system. The equation for this control system with unity feedback is shown in figure 2. This is the equation for the autopilot, which is cascaded with the aircraft dynamic. This is the equation for the aircraft dynamic. The value k can be assumed as 50. For the sub-question A, we are required to draw the boat plot of the system and determine the gain and phase margin of the system. As for sub-question B, we are required to design a compensator, either lead or lag, so that the phase margin would be at least 40 degrees. We decided to use Scilab to show our work. Firstly, we will be solving question A, where we need to draw the boat plot and determine the phase and gain margin. Since our equation is polynomial, we need to declare variable s as polynomial. We can see here in the variable browser where s is declared as polynomial. The second step is to calculate our equation. We can use any variable to declare our equation. The syslin is a linear system. This is used to create a list and check the consistency of data. As for C, since our equation is continuous time system domain, we use the variable C. If our system is discrete, we can use variable D, and this is our equation. The third step is to draw the boat plot. CLF is to clear the figure just in case to avoid it from mixing with our previous work. As for boat, here is to show the boat plot, and H is our declared equation, and 0.01 and 1000 is the range for our x-axis and y-axis respectively. Here is our boat plot. This is our magnitude graph, and this is our phase graph. To determine the phase margin and the gain margin, we can use this command. P is for the x-axis and frequency is for the y-axis, and type in this P underscore margin H. Here is our value for the frequency and our phase margin 26.94. For the gain margin, we need to type G for gain and change it here also to G. After that, we can get the frequency, and as for G, we will get infinity. To show the margin on the boat plot, we can type in this command: show underscore margins, open bracket H, comma, and boat, close bracket. Here we can see the plotted gain margin and the phase margin.
Hi, my name is Nur Afika Kwe binti Muhammad Daniel Kwe, and I will cover the section on designing a lead network. So the first step in designing a lead network is, first we have to identify the phase margin and also the gain crossover frequency. This is the gain crossover frequency. So the unit we obtained is in hertz. So first we have to convert this to radian. We can do this by multiplying 1.017 hertz times with 2 pi. We will obtain 6.39 radian. Okay, so in the next step, we will have to find the phi max. So the phi max is actually the required addition for the phase margin, and so according to the question, we need that the phase margin would at least be 40 degrees. So the phase margin need to be at least 40 degrees. So in this case, in order to find Vmax, we will first need to get the PM, which is the phase margin needed. So in order to get the phase margin needed, we have to get the 40 degrees, which is the required phase margin. So we have to take 40 degrees minus with the current phase margin, which is 26.94 degrees. So through this, we will obtain 13.06 degrees. So the phase margin needed would be 13 plus 0.6 degrees. However, we have to add another 15 degrees, which is the safety margin. So the total would be 28.06 degrees. So now the third step is solve for alpha. So we need to know the value of alpha. So by doing this, we first need to know that our Vmax is 28.06 degrees. Since after adding the safety margin, this is the lead network, the amount of Vmax for the lead network that we need to add on. So first, we have to get the formula, which is Vmax is equals to sine inverse alpha minus 1 over alpha plus 1. So now we already know the value of our Vmax, which is 28.06 degrees. So we can equal it to 28.06 degrees. So we have to bring the sign over in order to leave alpha at one side. So by doing this, we will get alpha minus 1 over alpha plus 1 is equals to sine 28.06 degrees. So by solving this, we will obtain alpha minus 1 over alpha plus 1 is equals to 0.47. So now we have to bring this over here. So it will be multiplied to obtain 0.47 alpha plus 0.47. So now we have to group the alpha at one side and the numbers at one side. So by doing this, we will obtain alpha minus 0.47 alpha is equals to 1.47. Since minus here brings over is become add, so we get 1 plus 0.47 is 1.47. So now alpha minus 0.47 alpha will result in 0.53 alpha, which is equals to 1.47. So by taking 0.53 over here, which is divide, we will obtain alpha is equals to 2.77. So now that we've already calculated alpha, the next step is we have to calculate the number for tau. So let's first list back the values that we've previously obtained, 6.39, and alpha is equals to 2.77. This is in radian. Okay, so the formula, in order to find tau, we have to equate the gain crossover frequency in radian, which is omega m. We have to equate it with an equation. So I have to do omega m is equals to 1 over tau square root of alpha. So now we already know our value of omega m, which is 6.39. So by doing this, we can actually find tau, and we have to do this by switching these two values. So now we will get tau, so alpha is equals to 1 over 6.39. So calculating this, we will obtain, tau. By doing this, we will obtain tau multiplied by alpha is equals to 0.16. So now we know that alpha is actually 2.77 square root. So we can say that tau is equals to 0.16 square root 2.77, which is equals to 0.16 with 1.66. So by calculating this value, we will then obtain tau is equals to 0.096. Okay, so in the last part, we have to rewrite the Lie network transfer function in the following form. So the last step is to rewrite GCS is equals to 1 plus alpha tau s over 1 plus tau s. So now we just substitute the value of alpha and tau into the equation, which will get us 1 plus alpha is 2.77, so it's 2.77, and tau is 0.096. So again is 0.096, and s, and this whole thing is over 1 plus tau again is 0.096, which is 0.096 s. So we can simplify this part to become GCS is equals to 1 plus, so now 2.77 we multiply by 0.96, we will obtain 0.27. 7s over 1 plus 0.096s. So this is the new equation that we've obtained, which is the Lie network transfer function.
Assalamualaikum, very good morning. My name is Siti Hazika Akilah binti Muhammad. We need to do the pre-merge inclusion using Scilab. First, use this equation to avoid of using
present as every time we use as later. Include numerator and denominator of the equation of the equation, and then include numerator and denominator of autopilot equation. C is equals to 50 as stated in the question, and this the numerator and denominator of aircraft equation. Next, include the equation for calculation, system line, and lastly display the phase margin using phase margin GCF equals to phase margin H. H is the value calculated using by using this equation. So the phase margin is 47.045255 or 47.05 degree.